All right, can you see my screen?
Yes. Yeah, we see your screen.
All right. Um, all right. Well, thank you for attending. Let me just minimize this. So yeah, I'm going to be talking about economic modeling and some work I've been doing with my collaborators. Matteo Scarselli, who's chair of mathematics at McMaster University in Canada, and Steve Keen, who's a bit of a renegade Australian economist. He's funded through Patreon and does very well that way, sort of trying to poke holes in neoclassical economics. And then there's myself, a snowflake scientist. So I don't know, I think it sounds like the beginning of the makings of one of those, three guys going to a bar joke. But there we are, collaborating in Deer Valley a couple of years ago, working on a project that was funded by the UK National Institute of Economic and Social Research, trying to integrate energy and matter into traditional economic models. So economics is at the core of what we do in terms of climate projections. We have these models. This is from the IPCC AR6, that just came out, of various scenarios ranging from what we might playfully call burn baby burn, a high emission scenario, to a low emission scenario with kumbaya, my lord. And these are what we use to imagine what might happen in the future with regards to climate change, such things including sea level rise and, let's say, global ocean surface acidity, with a very wide range of possible outcomes. Now, economists have gotten involved with this work as well as climate scientists. And in fact, there's been a great deal of collaboration between the two groups. And William Nordhaus in particular got actually a Nobel Prize in economics for his work trying to develop models that synthesize climate science into economic science into climate science predictions. And this, work that's fairly old, it goes back to, let's say, 1992. And here's like an illustration showing a projection, including the global economy, that what would lead to a particular temperature increase. And then acknowledging that abatement strategies, those that might limit carbon dioxide emissions, would cost money, he turned it into an optimization problem. How much should we spend in order to optimize economic growth, allowing for the fact that economic growth itself will lead to climate damages? And that is shown here by these square plots right here. So these models are rather core to our projections. These integrated assessment models is what they are known as. For example, here is from Nordhaus's 2017 paper in PNAS, which shows, for example, his DICE model. This is his creation, a couple of manifestations showing the predicted temperature rise compared to, let's say, the high emission scenario, the burn baby burn scenario that I presented earlier. And you can see that due to such things as carbon abatement strategies, it's a little bit lower than what you would get with the no constraints scenario. And then from this, what is created, as I mentioned, is this optimization problem. Now, the optimization problem, let's say we take the baseline being the gray curve, would be a lower curve. It would lead to a reduction in future global warming, depending on how much money or what the cost is that is imposed by governments on carbon. So there's a little table here on the right. If the cost of carbon is low, then there is a reduction in the future temperature increase because there are abatement strategies to achieve, let's say, a goal of let's say 2 degrees maximum warming, then the model identifies a much higher cost of carbon that must be imposed by governments. And so, on the face of it, this actually looks like a pretty nifty tool. Here we have something where we have a coupled system between the economic system and the climate system that allows for various policies that can be invoked to achieve a particular goal. Nothing on the face of it seems objectionable to that. And in fact, many people do believe that DICE, the model that's used here, is a useful tool. However, there is wide dispute about what the damages are of climate to the GDP. And this is something that lies at the cornerstone of these models. Because if you want to abate climate change, and you do not believe that damages to the GDP are high associated with climate change, and we don't have to spend as much as if you believe that the damages are going to be high. And then, this is an optimization problem again, but one that is a function of the percent reduction in GDP as a function of the temperature change of the planet. And as you can see, these are all very, very well-known economists. They have widely divergent views, ranging from a very small difference, you can see the red line presented by Nordhaus, to that from Dietz and Stern, which projects that for a 5-degree warming, the GDP is reduced by 80%. Now, you might think that this is catastrophic. An 80% reduction in GDP, that sounds catastrophic. But hold on, there is a caveat that must be made here. Now, the damages here that are presented are often expressed as a quadratic. On the y-axis I have here is a GDP damages relative to no climate change. So these are not the GDP damages relative to today. These are the GDP damages that would happen relative to what they would have been otherwise, adopting continued economic growth. Now, that is a very, very key thing. Now, again, the projected damages, depending on the model that is used, the economists that consider it, are all over the map. But we have Nordhaus, the one who won the Nobel Prize, who says that including all factors, the damage equation in the model assumes that damages are 2.1% of global income at 3 degrees Celsius warming and 8.5% of income at 6 degrees Celsius warming. I think that seems very low, perhaps, but it is even lower when one considers that the GDP, when we reach 6 degrees warming, if we do, is projected to be much higher than today. So let's look at this. These models have gone into a widely used tool called Nroads. I mean, some of you may be familiar with this. It's this interactive tool where it has all sorts of dials that you can turn to see what the projected temperature change will be by, let's say, changing our energy supply, changing things like efficiency, changing population growth and economic growth, all sorts of fun things. Now, in this model, here is the baseline model, which is that the GDP per capita, as we go through to 2100, will rise from about $10,000 per person per year on average across the globe to about $68,000 per person per year. At the same time as the temperature globally rises from about 1 degree above pre-industrial to 3.6 degrees Celsius, pre-industrial. Now, let's add the Nordhaus point of view. So that 8.5% at 6 degrees Celsius. Well, here is Nordhaus's view. It's shown here at the bottom, reduction in GDP at 2 degrees Celsius from climate impact. Oh, this is from Dietz and Stern, sorry, which is, remember, this was the high-end one that I showed previously, which is we have 2.6% damages at 2 degrees Celsius warming. Now, in this case, with these damages, the GDP per capita is lower than it would be otherwise by quite a lot. But notice it is still about 5 times higher than it is today. The temperature change is still very high in 2100, 3.5 degrees Celsius. The the Nordhaus model, on the other hand, is 0.9% at 2 degrees Celsius. So that's a much lower damages than the 2.6% from Dietz and Stern. And in that case, there's virtually no difference to warming and virtually no difference to the GDP per capita. So there, we are much richer. Our incomes are about 6 times higher than they are today. And in fact, with this model, the Nroads, we can actually switch to economic growth, shown at the bottom here. We can put up the dial, allow for more economic growth. And then our per capita income would increase from, let's say, 10,000 to 120,000, or about an order of magnitude higher. And the temperature is 4.1 degrees Celsius higher. Well, you might say, hold on. In a 4.1 degrees Celsius world, we don't all get private jets. Doesn't make a whole lot of sense. Remember, what Nordhaus is saying is that including all factors, the damage equation in the model assumes that damages are 2.1% of global income at 3 degrees Celsius warming and 8.5% of income at 6 degrees Celsius warming, below what it would have been otherwise, which is about 6 or 7 times higher than it is today. All right. I think in climate sciences, we see things rather differently. By the end of this century, the temperature will have increased by as much as it was colder 20,000 years ago. And the author of XKCD had his neighborhood under half a mile of ice. Different planet. Indeed, our civilization has evolved economically over a time period where temperatures were remarkably stable. And now we're looking at temperatures heading towards, well, again, a different planet. Something where at the very least, there are previous time scales. There was adjustment periods, but beech trees in Antarctica, alligators in the Arctic, not the same planet. Again, let's look at 4 degrees Celsius. This thing that Nordhaus says was actually an optimal increase. This is the temperature map here. It's a different planet. Precipitation change, different planet. And perhaps most relevant from an economic standpoint, let's look at the total column soil moisture change, which is that we see here in this different planet of 4 degrees global warming, tremendous aridification over grain belts in North America, Europe, and China. We still are 6 times richer.
He is lagging a lot, isn't he? Is he lagging a lot for you guys?
Sorry, what was that? Michelle? All right. So, these things are important. I mean, we talk about droughts. Already we're seeing droughts. In the 4 degrees Celsius world, we're talking about droughts that are 4.1 times more likely to occur and will be 1 standard deviation drier. These are significant events. And so, what we have here is really a tremendous academic divide. And I think it's only just starting to be recognized. We have atmospheric scientists like Tim Lenton saying there's currently a huge gulf between natural scientists' understanding of climate tipping points and economists' representations of climate catastrophes and integrated assessment models. And even on the economic side, there may be some allowance. Here from Stern and Stiglitz, the fact that the overwhelming consensus in the scientific community differs so markedly from the results of the integrated assessment models raises a key question. Is it sloppy thinking? Is it us, atmospheric scientists, that has led the international community to irrationally embrace a goal involving excessive costs from the perspective of a hard-headed analysis of a society welfare maximization? It is us scientists that are asking us to spend too much for abatement. Or is it, perhaps, that the IMs have left something or many things out of their analysis. So at least there is a window that is being opened here to an adjustment. So before I go on, let me just check my battery, 27%. Okay, that's good. Oops. So in this collaboration and with a couple of others, including Tim Linton, but also Stephen Keen and Matthias Grasselli, we wrote a paper called Economists' Erroneous Estimates of Damages from Climate Change. And the conclusion in the abstract is that given these flaws, economists' empirical estimates of economic damages from global warming should be rejected as unscientific, and models that have been calibrated to them, such as DICE, should not be used to evaluate economic risks from climate change or in the development of policy to attenuate damages. So perhaps predictably, the paper got rejected, but we've appealed. We'll see how it goes. But that's par for the course of this sort of material. So DICE, well, it's a complicated model, lots of stuff going on. I'm not going to go into all these details, but I'm going to go over a few key things where I see as being particular points where the models DICE has got things wrong. One is that damages to the GDP are trivialized. They're obviously phony. The damages are not cumulative. So civilization collapse in these models is not a mathematical possibility. These models like DICE will happily have the economy keep on growing with no stop. And then there's a built-in assumption in these models that the economy can decouple from resources. So let's first look at this trivialized damages thing. So, I mean, you think, 8.5 degrees Celsius, damages for 6 degrees Celsius. I think most of us would think 6 degrees Celsius, we're not left. We're not here. It's not 8.5%. We're gone. How did Nordhaus get this estimate? So it turns out they did something that on face value sounds rather clever, but that on deeper thought seems really pretty absurd. So what they have done is that they make the assumption that the observed variation of economic activity with climate over space holds over time as well. So let's look at this figure here. This figure shows the per capita income of people for all the states in the United States. So some states have higher incomes than other states. And then they compared that income versus the temperature deviation from the USA average, which is 11.5 degrees Celsius. And so you've got these red points here. And I think you see a scatter plot here, and you'd say, well, I think your first guess would be, well, there is no correlation. But nonetheless, what they did is they fit a quadratic to it. And naturally, because there is no correlation, the quadratic fit has, well, A, a low correlation, B, it's a weak function. The square right here on the right is the value that Nordhaus is using for his 8.5% damages for 6 degrees warming. You think about this, well, I think a gut reaction would be, okay, this is crazy. Why would you relate the temperatures in states to their incomes and then project into the future? And it takes some thought, I think, to realize it's wrong. And I think the basic thing that is wrong is that these points are not independent. If you took, let's say, Alaska or Florida, without trade with, say, Iowa, Alaska and Florida would be tremendously poor. So you cannot draw a correlation between those two places and treat them as statistically independent. Moreover, those incomes of those places in Alaska and Florida are higher because of trade, but while we can trade in the present, we cannot trade through time. So while the climate may get warmer, we cannot trade in the past to get food from a more favorable climate, say, back in today's years to feed us in 2100. Moreover, in 2100, Iowa may have experienced such aridification that's not available to trade with anyhow. And the topsoil certainly isn't in Minnesota. So this seems fundamentally problematic, yet it lies at the basis of the sort of predictions of damage functions that are used in the future. So, so there I had that right here. All right, well, now let's go a little bit deeper into how these models work. And here they have a basic engine, a growth engine that's worth looking at. And the way this works is that they have economic GDP happens because labor uses physical capital, sort of our infrastructure, buildings, cars, whatever it is, to make stuff and services. Physical capital grows due to economic production. So when we make stuff, that adds to our, the stuff that we have that we can use in the future to make more stuff. And then there's also some that's lost due to short-term consumption and depreciation. So only some is saved for the future. Labor grows, well, because birds and bees, it just grows. No questions there, at least in the models. And then there's an added ingredient, which is that climate change damages economic production. Okay, well, let's put this a little bit of math into this, which is that we have a function here for an economic growth model. Economic production, Y, is the symbol that's used for economic production, is due to labor and physical capital. So some function of those. And it's a very complicated, rather bizarre, dimensionally inconsistent function, but there it is, that's the function we use. Then capital grows due to savings, which is about 20% per year of production, Y. So that's what allows for capital to grow at rate dk dt, k being the symbol for capital, but also capital depreciates with at a rate of delta, which might be 5% per year. Now, what Nordhaus did was to say, okay, this model's fine, but I'm going to add an extra term. And that extra term is to take the production equation, again, it's a function of labor and capital, as shown right here, but then there's this damage function. And the damage function is a function of how much the climate has warmed. So the climate warms, 5 degrees, then there's a quadratic function that determines the nature of damages so that the production is not as high as it would be otherwise. Meanwhile, the capital growth equation stays the same. And I think you would look at this and perhaps scratch your head and say, well, okay, damages to production, okay, that's fine. We're not productive because, well, it's harder for us to be productive. It's too hot or whatever. But where's the damages to infrastructure? Shouldn't there be damages to infrastructure in this? I mean, sea level rise will eat away at buildings, road coastlines, eat up land. It will affect people's ability to work. So labor gets diminished. But this is not what is in the models. And because of this, what is forbidden in the models is a phenomenon that I like to call death by 1,000 cuts. We do not have the capacity for collapse in these models because there is no gradual erosion of capital within these models that accumulates with time that would then feed back on the ability to produce new capital. So we could end up in a situation where whatever we produce simply goes to repair. And then eventually there is so much to repair that we cannot keep up and we stop growing, we enter into a phase of collapse. So I tried to do this. And I said, well, could we create collapse? And I sort of switched it around. Say, rather than damages on economic production, let's make the damages due to climate change like a depreciation term, but an added term due to climate change is due to capital being damaged rather than production being damaged. And it turns out if you do that, that capital damages over and above depreciation, which is about 5% per year, of just 2.4% per year would be sufficient to tip the economic system towards collapse, even in the absence of damages to output. We do not have to do that much extra to cause civilization collapse. Now, this is a very simple model. I think an economist will look at this and say you're being overly simplifying things, but nonetheless, the point here is that where Nordhaus has things growing to infinity, quite quickly, if you just switch the damages to capital rather than production, the picture entirely changes. So, am I being too critical of Nordhaus? Well, yeah, perhaps I am, but let's take a look at who he shared the Nobel Prize with. Paul Romer, whose work actually I rather like in a lot of ways. And what does Paul Romer have to say about the field of economics? Well, Macroeconomics, then, a general failure mode of science that is triggered when respect for highly regarded leaders evolves into a deference to authority that displaces subjective fact from its position as the ultimate determinant of scientific truth. Ouch. The trouble is not so much that macroeconomists say things that are inconsistent with the facts. The real trouble is that other economists do not care, that the macroeconomists do not care about the facts. An indifferent tolerance of obvious error is even more corrosive to science than permitted advocacy of error. I think it's a very interesting statement, and coming from an economist, quite damning. So, work that I did with Matthias and Steve Keen. We had a paper came out in PLOS One, just to show that I'm not randomly criticizing things without trying to do something myself. We do actually have our own economic model that I've been developing over the past 15 years or so. And here I'm trying to invoke physical constraints, trying to think about very simple physical systems like the growth of a snowflake. How does it grow? Can we take this sort of very simplified model, which I might understand as a cloud physicist, and apply it to the global economy? Thinking about, this is a multifaceted beast, and that it does display features of growth, accelerating growth, with some features growing more than others. Or let me just look at my teenage son here. He's a bit younger here, but how did he grow? Well, here there's some key features. And the past is absolutely critical to understand. Things like inertia. His current consumption is tied to his past production. He consumes energy, he consumes food. He's now, I don't know, 6 feet, 6'1". How did he get to be so consumptive? Well, he was consumptive because he produced body mass over the past. There was a disequilibrium that allowed for a net convergence of matter within his body, production. I won't call it economic production, but it's body production in his case. That's analogous to economic production. He's producing infrastructure, body capital. And because he did it efficiently, he was able to grow rapidly to consume more energy today than he did in the past. Note that he was efficient, but the efficiency led to more growth rather than less growth. And now if he wanted to consume much less, well, he can't. The past is with him. He is stuck with that prior 18 years of growth that has led to his consumptive state and dissipative state. So here we are with civilization, with all its networks that are sustained through communication networks, plane networks, shipping, whatever it is. And all of this requires energy. Even if we no longer grow, even if there is a stasis, even if there is no net production, we still have metabolic needs as a global organism that require that we continually consume energy. And those metabolic needs are not tied to the present so much as they are tied to thousands of years of civilization evolution that have led us to the point we exist at today. So with that concept in mind, I created a new economic quantity, very much not widely accepted or known, but that I defined a quantity that I called wealth, W, defined as a cumulative time integral of prior economic production, adjusting for inflation. So if the world economic production is the black curve, then the integral is the area underneath the curve. And that is some representation of everything that has been done in the past to lead to the current state. And what I showed is that if we start, let's say in 1980, and I've taken this back to 1970, that if we look at the time, initializing with everything at 100, if we look at economic production, that has grown. If we look at energy consumption, that has grown too. The two are correlated, but the ratio of the two has declined as we've become more energy efficient. But if we look at the ratio of energy consumption to cumulative historical production, that ratio, on the other hand, has stayed fixed. And I think that is a very important result, that there is a fixed relationship between our current energy demands and our cumulative past production. And this is what we can use to guide the future. Ultimately, there's a constant 5.8 gigawatts of power production capacity is required to sustain each previously accumulated trillion 2010 US dollars of real gross domestic production. So that leads to a CO2 emissions identity. If we will want to look at our emissions, we have a carbonization of the energy supply. We can multiply that by our energy consumption rates. We can relate that to the history of economic production through a constant lambda and the carbonization, this being a time integral. This is the past. Current emissions are not tied to the present so much as they are tied to all of the past. So the conclusions, without decarbonizing, emissions cannot be reduced without destruction of global wealth. We cannot decouple the economy from resources. Also, current emissions are tied to past history of real GDP. Past can't be erased. We're kind of stuck, like my son, with consumption. Civilization fundamentally has inertia to its consumption. So I'm not going to describe this in detail, except to say that it is possible on the basis of this, with non-equilibrium thermodynamics, to create a very simple model, not dice, but something simple that has an economics module, an atmospheric model, and an economic growth efficiency model that can be tied to resource discovery and depletion. And this very simple model can be tested. I've done this. I've taken the model and initialized it with the 1950s, starting in 1960, and was able to predict economic growth, the GDP growth rate to 2010, energy consumption to 2010, and CO2 emissions to 2010 with, I think, a skill score in the high 90%. And with this sort of model, one can make predictions. Where are we headed? This is an alternative viewpoint from the models that the IPCC is using. This is rather old. I don't have enough time to do this stuff and update it. But these blue lines are the sort of things that the IPCC model is using. A1F1 you could think about as being RCD 8.5. The models I would use in this space of atmospheric carbon dioxide concentrations and gross world production show a business as usual model, takes us up to CO2 concentrations above 1,000 parts per million in 2100. But those do not, that assumes that we are completely resilient to climate change, which is improbable. So we have going along this axis scenarios where our resilience is weakened. Here would be 1% loss of, say, capital per year due to climate change. In this case, we can see that civilization gets creaky. The GDP gets creaky. And depending on how resilient we are, we could, in fact, in this model have collapse, which DICE does not allow for. Point just simply being, there are alternative approaches up there that can be used that are constrained by physics. And that the SRES models get an unphysically high GDP per CO2 because they assume that energy consumption can be decoupled from the economy through efficiency gains, which I do not see as being the case. So here we are. We come up with policies, many policies, over time, many agreements, and we're surprised when they don't seem to do anything. We continue to march up at ever accelerating rates to higher CO2 concentrations. Why is this? Why aren't we asking this? You know, I think fundamentally this is a geological problem, that ultimately this is a question of what reserves are out there, how fast do we discover them, and how fast do we deplete them? We have a timeline here. This is just the data I could get, and I got it by accident. But we have gas and oil reserves here available to the world. Now this is just gas and oil. I realize that's a limitation with the year. And we see that we have time periods where discovery was was rising incredibly quickly. We were consuming, but we weren't consuming faster than we were discovering. Now, 1950 to 1970 economically was crazy. Everything went gangbusters. And then since then, things have become more competitive because we are continuing to discover new reserves, but we are consuming them just as fast. So what remains is stagnating. What does that imply economically? I mean, I have ideas. What does it imply for the carbon dioxide in the future? I mean, you know, again, I think there are possible ways to predict this. But again, it's not dice. If we are going to use these models here, these models should not be used if they are physically unrealistic, if they're based on integrated assessment models that do not incorporate physical constraints. And this is a fundamental problem for our field because we do want to constrain the future. We do want to get an idea of the predictor. We are in the prediction business, but we cannot do this as long as we're using economic models that are not tethered to reality. So 3 problems with DICE. Damages to the GDP are not trivial, and damages to the GDP should be cumulative, as they are with the capital. And also, the economy cannot be decoupled from resources for basic thermodynamic reasons. We cannot survive without raw materials and energy. So, in conclusion, a little quote from Einstein. Thank you very much.
Okay, so you any question for Tim?
Hello, Tim. Can you hear me?
Yeah.
Yeah.
Yeah, it's Richard Nalthanius here.
Oh, hi.
Yeah, hi. I don't think we've actually spoken yet, but as you know, I'm a big fan of your work. So you've made some claims there about the DICE model that actually, is that really true that it decouples completely the GDP from resources? It just assumes that you can produce magical GDP without mining and all the rest?
It doesn't decouple to zero, but all these models have. So perhaps what I can do here is, again, as I'm sharing my screen, I can show you because I have the Nroads model here. Nroads. All right. So let's say we look at Nroads here. I could do things like here, well, here's net emissions. It's a bit hard to deal with, but I could do something like increase the energy efficiency. If I increase the energy efficiency in these models, net emissions go down. And energy efficiency is defined here as the ratio of the GDP to energy. If we become more energy efficient in these models, we are able to consume less in the future. Now, based on this relationship that I showed between what I called wealth and energy, it turns out the opposite is the case. It's just like a growing child. A healthy, robust growing child is energy efficient. It can take the energy of food and efficiently convert it, the food matter, into body matter, so that it is able to exercise net growth of its body mass. Mm-hmm. If its body mass grows, then it consumes more energy in the future. If it is less energy efficient, well, then it's a sickly child and maybe it even dies. And so the difference is fundamentally whether or not the system boundaries can change, grow and shrink, or whether they are fixed. If they are fixed, then yes, a more energy, like a car, a more efficient car will consume less energy.
So you're saying the
engine size. We are.
Yeah. Right. So you're saying the decoupling by basically varying one thing at a time in the model and seeing in effect what it does.
Yeah. It's not rather that efficiency is a driving force of growth.
Yeah. Is there any effort to, I mean, I'd love to have an Nroads that actually works. And I came to the same conclusion you did, that the results were ridiculous. And so I don't want to use it in any of my classes. But do you know of anybody who's trying to, let's say, reconstruct it from more, the ability to put in more realistic assumptions, for example, coupling wealth to current power consumption?
Well, I
No.
mean, the thing is, what I just described is utterly fringe. There's no financial support for it, and support.
Well, that's sad.
Here and there. All these things do not develop because, well, all the rest of us have day jobs.
Yeah. Yeah. Well, I've had the same problem. As you know, I have worked with your work for a while, and my progress is slow as well because I'm a one-man department. So it looked like there was another question perhaps coming.
Peter Will.
Yeah, that's me. It's Peter. This was really nice, Tim. I really enjoyed the seminar. Yeah, I hadn't really considered this intersection between economics and atmospheric science, and was just wondering if you've tried to bring this to the economists as far as seminars for those folks.
Well, try to publish papers, and it goes through a review process and ends up leading to rude remarks from economists. I'm collaborating with Steve Keen. He's a bona fide economist. Matteo Scarselli is a mathematician, but his work is in finance and economics. He works very closely with Steve Keen at developing basically predator-prey models for economic systems, and then trying to tie that into energy and matter.
Right, but have you tried to give a seminar at any of these departments where, perhaps Nordhaus or others are?
Well, no one's invited me.
Yeah,
I wonder why.
Might be worth.
I've given various. I just gave a podcast yesterday, and there's stuff like that helps get things out. But yeah, it's not very. I think one thing that Nordhaus's models did, as I mentioned initially, the premise is actually quite nice. How much do we have to spend to address this problem? It's just that it was done in an atrocious way.
Mm-hmm. But so atrociously that it's pretty important that a lot of this is out into the wider field, I think.
Well, I will say one thing. Steve Keen, when I introduced him as being a renegade economist, he's not held back by regular academic niceties. He is self-funded, and he's Australian, and he says what he thinks. So that helps get out the message.
Mm-hmm.
Okay, so there are also
he has a pretty big following.
Okay, there are also questions on chat. Will Fabrother?
Sorry, what was the question?
The question, any idea when the paper with Lenton King will be published?
Well, yeah, I submit to proceedings of the Royal Society. Yeah, I got rejected, but hopefully it'll be, we appealed. Hopefully it goes back through the appeal process. I don't know what I'll do. There was a paper out by Dietz, who I mentioned, who talked about tipping points in the climate system, and the paper just out of PNAS. And bizarrely, he represents tipping points in the climate system economically using, again, a quadratic. And I think you don't think about a quadratic being as a sort of thing that would be used to represent tipping points. Nonetheless, that's what he used. And he only had 100% damages to GDP at 17.68 degrees Celsius warming. So, you know, a bizarrely precise number. And, well, 100%, I don't know. I mean, it's hard not to laugh. I mean, 17.68 degrees Celsius. I'm sorry, we have economy at 17.67 Celsius. Anyway, we wrote a letter to PNAS criticizing this paper, and that may come out.
Okay, I see the hands rising for Matheus Gracio.
Yes, hi Tim, Matthias here.
Hi, Matthias.
I'm coming to respond to, I think it was Peter who was asking about giving this type of seminar to economists or to finance people. So I'm not nearly as well known as Steve, but I do give talks in places like the OECD, because they have an interest there in developing this kind of models, or at least contrasting the models with the models that the more traditional economists have. And the reception, sorry, I think there is an echo. Maybe, yeah. The reception that I get is that, you know, the traditional economists, the default response is that, oh, sure, you're criticizing these models, but these are the early models. You know, DICE was done in the 1990s. We have moved on. We have much more sophisticated models now. And that's at the heat of the moment in the middle of the seminar. And then what can you do? You know, you cannot dissect the claims in the 5-minute question and answer period. But then you go on and look at the papers that are coming out now, like 2021. Tim just forwarded to us the link of a paper that Nordhaus published in PNAS now. And it's what he calls a C-DICE. So it's the DICE model taken into account correlations and competitions between countries, but at the core is the same DICE model. So it's just adding a couple of bells and whistles in there, make it a 2-region model and so on. But the treatment of damages, the treatment of, you know, how to estimate the future damages based on the present spatial variability with temperature, it's all there. It doesn't change. It's the same basis. So it becomes this funny game that they say, no, what you are criticizing is a straw man. The real thing is much better. And you look at the real thing and it's the exact same basis as the straw man. So it's a little frustration, but hey, we're trying.
Thanks, Matthias.
Okay, Golden. Golden has a question. Limits to growth models.
Sorry, what was the question?
No, it wasn't really a question. It was a reply, because I think Richard asked if there are any models that account for all energy and stuff like that. And I was replying that the limits to growth models, they have quite, in my opinion, sophisticated ways of modeling the economy. And yeah, was just pointing to that.
Yeah, so the limits to growth models, this is something that was back in the early 70s when it first came out. Late 60s, early 70s, and Nordhaus was extraordinarily critical of limits to growth. These models that, you know, suggested that there might be resource constraints that, you know, could lead to collapse. And, you know, that was, I guess at that time, enough of a heretical idea that it really was poo-pooed by Nordhaus. And Nordhaus, I think, was quite effective in sort of stopping consideration of limits to growth as a modeling framework. And my own view of the limits to growth model is that it does have physical resource limitations that are considered. It isn't fundamentally a physics model, as, let's say, the approach that I try to take. nonetheless, I think it does work in, kind of the right direction. Whatever its limitations may be, and let's say the coefficients for various parameters in it, it is still a moderately complex model. It does do key things that the DICE model does not do, which is actually allow for collapse. Now, if a model does not allow for collapse easily within some range of parameter space, I don't know what the model is. It's not a model that represents reality in any sense. All systems go through phases of growth and then ultimately collapse. So if you cannot tweak the model mathematically, even somehow, and have that happen, I don't know what it means.
Okay, any other question for Tim?
Yeah, I've got one. I just put it into the chat there. So, so one of the things that I tried from your early papers was including the so-called shadow economy in the GDP summation. And as long as that doesn't vary strongly with the total economy, then the constancy of lambda is preserved. However, I'm thinking that isn't necessarily going to be true in the future. And so that it perhaps should explicitly be put in. I'm thinking of Bitcoin, for example, as something that's not as easily added into the nominal GDP values you'll find in the data.
Yeah, so when you refer to the shadow economy, you're referring to things like, I don't know, say the black market or things like that. And yes, very much you may be right. I mean, the expression that I consider for, let's say, that wealth parameter is some, it assumes that there's some relationship between the GDP and actual, physical production of some form, like whether it's of a potential civilization or of its material production. I'm starting to think more that it is much more material production, because the potential civilization, I think, is fundamentally governed by the daily cycle. So that is pretty fixed. So let's see, Bitcoin. Is Bitcoin part of the economy? Well, yeah, in some sense it is. Is it leading to net production, growth, manufacturers of goods and services? I don't know if that's as clear. Nonetheless, I would just simply agree with you that, these are questions that I think are good questions and should be asked more, but the resources simply are not there currently for anybody to look at them. I mean, it's just a few of us tinkering on the side.
Yeah. Yeah. I've talked with some good economists here at UCSC too, and they're also not interested in following this up, despite my excellent presentations to show them that there's some value here. It's a commentary on the world, I guess, what drives us mentally.
Okay, so I see hands up, Siri.
Yeah, hi there, Tim. I'm phoning in from the UK here today, so it's a bit late this end, but I really liked your talk, and I kind of feel I come at this from a system science background. I used to study climate cycle feedbacks, looking at runaway effects in the Arctic and things, and all my peers think that we're heading towards civilizational collapse if we don't urgently phase out fossil fuels. And so, there was this kind of this huge gap that you described between, what our community of Earth system scientists are saying and what the economic models are saying. And it was making me scratch my head thinking, well, what why is this so different? And I think you've hit your nail on the head. You've really explained just how poorly parameterized these models are in terms of the damage functions that they use and so on. My question to you is really about that last part where you were talking about the cumulative production and how that ties us into kind of really not being able to decouple resources from energy. Sorry, our economy from energy. I guess the point about decoupling is this idea that we can substitute renewable energy for fossil fuels, right? So it's the parameter of the carbonizing function in your equation. Yeah, that's it. Is that really, does that stop us from being able to decouple? I guess it makes the challenge harder, but also there's a lot of discussion around kind of trying to reduce energy demand. So through changing through degrowth as a kind of economic reform and not continuing to pursue expansion as our key economic game. Does your model allow for those things at all? You're on mute, sorry, Tim.
All right, so I mean, it's an excellent question, and I'd love to give it a second talk talking about these issues, and some extent I don't fully know the answer, but I would like to describe just a couple of things that I think is the way it probably will go. So let's say we take where is this? This must be on here somewhere. Do you see the energy here? So non-zero carbon. I think that should be it. If we could new zero carbon. Is that new zero carbon?
Well,
I mean, we have in Nroads things like this where we could drop. Well, they got renewables here too. We could increase renewables, new zero, and then that will lead to less warming because there's less carbon dioxide emissions. I think it's going to work the opposite way, and I think this is what we are actually observing, which is that the renewables have done the exact opposite of what people hope they will. As it has been in the past, new energy sources add, in fact, they may even enhance rather than replace. And for there, I would like to just draw a link to, again, I like physical analogs, simple physical analogs. I think everything in the universe is the same. So I can look at a snowflake and use that as a model. Here we have two ways of consuming energy, basal growth and prism growth. So basal growth is deposition on that face you see. Prism growth is the growth along the tips right here. Now, for this kind of snowflake that makes for great skiing, I have to turn on my car engine, sorry, battery's dying. For this kind of crystal, which makes for great skiing, prism growth is more efficient than basal growth. So imagine we had, for example, renewable energy that was more efficient, more desirable than the fossil energy source. Well, then we would see a growth of renewable energy. That would be indeed the dominant growth paradigm. However, if you look at the snowflake, the basal deposition onto the basal face is actually increasing with time by virtue of the efficient prism growth. It is because these branches are growing outwards that the basal face actually increases its area, allowing for greater deposition onto that face. Now, if that seems too remote to you, just look at what's happening. We have new renewable energy. Renewable energy allows us to use that energy, so just like food, to make more of us, to build more of everything demanding more energy of whatever sort, including fossil. So again, simple physical models, I think, make a lot of sense and are instructive and explanatory for what we're seeing, which is that we are seeing a surge of renewable energy, but we are not seeing us wean ourselves away from fossil fuels. Carbon dioxide emissions are continuing to rise or even accelerate. I think the best solution is I think Bitcoin mining is the best solution because it's utterly, totally pointless. It consumes fossil energy without leading to growth. So the best thing you can do is just waste the energy as quickly as possible, leading to rapid inflation and ultimate economic collapse elsewhere. And then maybe the planet has a prayer.
Okay, so are there any other question? I did not see any from the chat, and also no one hands on. So yeah, thanks. Thanks for Professor Tim Garrett again for the talk and the discussion. Yeah, so yeah, if you have further questions, just ask him offline. Thank you, Tim.
Very much, everyone.
Okay, so yeah, announcement. So this is our last seminar in the semester, and we conclude. And I thanks everyone for attending all seminar this semester. And I hope you have nice final week and also enjoy the holiday. Thank you very much.